replacement reactions. Double replacement reactions are going to be where you've got your cations, okay, and you've got your anions, and you're going to swap partners, okay. Your cation from this one is going to come over and be with the anion of this one, and the cation and anion from these two are going to come together. So do you see where we just swapped those here? Where that happened? Okay. Here, same difference, same thing. We got our iron. Iron is going to go here. The chlorine from this one is going to go with the iron, and the sulfur from this one is going to go with the hydrogen. Okay. Remember, we can rewrite this as HOH, and then this one will make a little bit more sense too. The hydrogen is going to go with the hydroxide, making water, and your calcium and your chlorate are going to go together to make these two things. So that's what we're doing as far as swapping ions around. Okay. Now, when we are doing this, what you have to do is you have to look and you have to see if a precipitate, a gas, or water are created. And that's what that chart is going to do for you. Okay. So we're going to go through some examples here to figure this out. Okay. So let's start with number 1 here. We have calcium. We have hydroxide. Oh, shoot. It's not an arrow yet. I got carried away. I'm going to do my arrow here. Okay. I don't like that pink. It's too close to the red. All right. So this is what I'm starting with. Okay. You assume that all of these things are aqueous. Okay. Meaning that if you had a container here, in that big old container, container 1, you're going to have calcium ions floating around, and you're going to have hydroxide ions floating around in there. In another container, you are going to have hydrogen ions floating around, and you're going to have phosphate ions floating around. Okay, so we've got these 2 containers here at the beginning of this. We're always going to assume that they're aqueous. Don't even bother to look them up on your sheet. Don't waste your time. You're just going to assume that these are both starting out as aqueous. Okay?
How come?
Because I tell you. That's how the double replacement reactions work. We're going to start them out as aqueous. Okay? So we're all going to be floating around. We've got 2 separate containers. Everybody good with that? All right. Now we are going to mix those together all in the same container and see what happens. Okay? And this is where your sheet is going to come in handy. All right. Our calcium then is going to go with what? Yep. The calcium is going to go with the phosphate. So they're swapping partners. You cannot put two cations together, they get in a cat fight, and life is not good. Okay? A cation has to go with an anion, and the cation always goes first in the listing. Okay? So I'm going to put that together with my phosphate. I need to balance these out. I have this as a -3, and I have this as a +2. So I need 3 of these for every 2 of these. Then I'm going to go and I'm going to take care of this. So my H is going to go with my OH, and you can write that as HOH if you prefer. I wish they would let you customize this so you could get different, get rid of these 2 things that I never use and put more pen colors up here. I've explored it and I can't find a way to make it happen. All right, so now you have to go to your solubility chart and figure out what this makes. Okay, so we're going to find calcium and we're going to find phosphate. This works similarly to a multiplication table. Okay, so I'm going to find calcium. Calcium is right here. Okay, and then I'm going to find phosphate, and I'm going to figure out where they meet. They meet right here, and that has a big N in there. If you go down to the bottom of your sheet, I have given you a key down here. This means that this is going to be soluble. This is going to form a precipitate then. That's what N in the box means. Okay?
Not soluble?
Not soluble, which means it's going to stay as a solid. It's not going to break up into its ions. Okay? So on your thing here, you are going to write an S in parentheses, meaning that that is going to form a solid. And what will happen is this calcium here and this phosphate here, they are going to come together and they're going to essentially form a powder down in the bottom of this beaker. And that's going to be your calcium phosphate. You did this in lab with the silver and the chlorine. Remember, you had HCl in one container, you had silver nitrate in another. You put them together in a test tube. Your hydrogen and your nitrate ended up floating, and then you formed AgCl down on the bottom. And that was the purple stuff that you filtered out on the filter paper under the hood. You also did this with, I think, lead and barium, I believe. Lead nitrate and barium something or other, and formed some stuff with that. Yeah, so you did this several different times. Okay? So this reaction, at the end, you have to go back and you have to see, did I form a precipitate, gas, or water? This reaction is actually going to run for 2 different reasons. Because you created a precipitate, which is this solid, it'll run. Because you created water, that's an L, it will also run. So this reaction is going to happen. Okay? I'm going to try to find one on here real quick. Yeah, here we go. Let's do no, that doesn't work. That's form sludge, carbonate, acetic acid, sulfite. Trying to find one here quickly that doesn't run. Potassium acetate, silver chromate runs. Lead nitrate, lead iodate. That probably won't run either. Copper sulfide, potassium sulfide, and copper chloride. Okay, I think this is a good one. Let me just check copper again. Copper chloride, copper. Yep, okay, good. Yep. So let's do this one. So we have copper 2 sulfide. Oh, no, they're both 2s. There. And we have potassium chloride. Okay. Again, in the beginning, we're going to assume that all of these are aqueous. I'm going to swap my partners. I usually put my cations down first, and then I swap partners. So the sulfur is going to go with the potassium here, and the copper is going to go with the chloride. And it was copper 2, so Cl2. Okay. Everybody good with that so far? Everybody understands where I got these 2s from? Anybody not? Okay. All right. Now we're going to go and check our chart. So we've got to find copper and chlorine. So on my chart over here, I'm going to find my copper, and there's copper 2 is right here. And I'm going to go over to chlorine. It says that it is an S. Now, this is the hard part. When you see an S here, that doesn't mean that you write an S down here. Okay. What do you write down here? AQ. All right. So be careful with that. That S doesn't mean solid. It means soluble, which means when this is put into water, it's going to break up into your copper ions and your chlorine ions. So that's what that S means. It's soluble. You are going to write down AQ there. That's why I put on your sheet here in my handwriting AQ. Okay? All right, now we're going to go back and we're going to look at potassium and sulfur. So let's go back to our list here. We are going to find potassium and we are going to find sulfur. That says S as well. So what do I write down on my sheet here? AQ, which means that my potassium and my sulfur are still going to be falling apart or floating around as ions. So if over here they were floating around as ions and over here they're floating around as ions, has anything changed? No. And that's why for this guy, you write no reaction. Because nothing's changed. There is no reaction. All that you've done is you've just mixed them in the same container. But they're still floating around. Oh, but they're all aqueous. Mm-hmm. Yep. So if it's all aqueous here, if both of these things end up being aqueous, then that means that you're not going to have a reaction because nothing's changed. They're still floating around in there. Okay. So if you form water, if you form a precipitate, which is, it'll say N or SS on your sheet, or you form a gas, then they're going to be, the reaction will run. Now, how do you know if you form a gas? If you go to this sheet, down at the bottom, we have listed for you common gases. So H2S is one, CO2, SO2, and then, of course, your Brinkelhoffs. All right. Isn't that making sense? Now, we have a couple special scenarios, which we have listed here. if you form either one of these, you erase that and you write this stuff in its place. Because this is automatically going to decompose into these two things. So let's try one of those. Okay, there we go. So number 6 here is Na2CO3, sulfuric acid. Oh, I didn't need to balance that equation because we didn't run. So I don't need to worry about that. All right. Did I balance the one up here, though? I never balanced this guy. You guys are getting comfortable enough balancing, though. I think you can probably handle that. All right. Down here, I'll balance this one for you, though. We'll get to it. All right. So we are going to swap partners. I'm going to put my sodium with my sulfate. And I'm going to put my H2 with my CO3. Hopefully you're writing in pencil. All right. Now, this is we're going to check this guy. So sodium and sulfate. We're going to go over to our chart here. We're going to find sodium. And we're going to find sulfate, which is in the last column. So right here, that has an S. What do I write down? AQ. Okay. Now this guy, we know that all acids are aqueous. How do we know that? Because I typed this in for you right here. All acids are aqueous. Okay. Now, if that was any other acid, we would be done and it would be a no reaction. But this is one of those special scenarios where we are automatically going to decompose into these two things. So I am going to erase this guy, and in its place, I am going to write H2O plus CO2. All right. This is a liquid. This is water. That'll make the reaction run. And this guy is a gas. That will also make the reaction run. So this reaction runs. Now we need to balance this guy. So I have a sodium. I have to split out my carbons and my oxygens because they're not the same things on both sides. The carbonate falls apart. My hydrogen's going to be here. My sulfate is the same on both sides, so I'm going to keep that together. I'm counting this oxygen here. I'm not counting this one because that's part of that sulfate. Okay, I'm going to count that as part of the sulfate when I do my tallies. Carbon, oxygen, I've got 1 here. I've got 3 there. And my hydrogens. And guess what, folks? It's balanced, right? Unless I'm still having a Monday? No. All right. So I'm good? All right. So those are the scenarios that you're working with. I want to call a couple things to your attention. And I wrote this actually on your sheet because this always ends up coming up every year. Chromates are usually insoluble. So almost all the time when you have a chromate, it's going to get an N in the box, which means you're going to write down solid for it. Okay? So this is one that people miss. They forget that this is on the back side. I also put down like your 8s and X down here just to kind of give you a reminder. This chart and this orange sheet you will have every time you take a quiz or test. You do not need to memorize anything on it. Are we clear? Okay. So don't get all worked up. Oh my God, I got to memorize. No, you don't. For AP, you have 4 things on here to memorize. They're all soluble, and I give you an acronym so that it takes you no time at all. Okay. So once you have that, you're not going to worry about AP because there's nothing extra to really remember in AP either. Okay. So breathe. All right. Questions about double replacement reactions? Okay. So let me find the quizzes that I just went and ran off and then promptly hid from myself. Here they are. And you'll have about